Thank you. And thanks for planning the wonderful workshop. It's been really fun so far. In thinking about this talk, I realized I probably should have titled it something a little bit more interesting, maybe like Confessions of a Lapsed Realist, because I'm going to sort of go through, I guess, two of my favorite forms of realism and some of the problems that I've encountered in trying to make sense of them. So here is a little, okay. So here is an outline for the talk today. So to begin, I'll talk about sort of two general perspectives on the fact of science. Generally speaking, I guess realism and idealism and some of the problems that I want to focus on in the talk. Then I'll briefly introduce structuralism, perspectivism in a little bit more detail. And then I'll try and get to Cassirer and some neo-Kantianism and Cassirer's take on the methodology of mathematical physics and a case study for mathematical physics. And then I'm hoping at the end to bring it all together to give sort of my last ditch effort at securing a form of realism that I guess I would be comfortable with, given sort of the commitments I have shared with Cassirer. So to begin, I want to just talk about sort of the two major approaches to what I would call the fact of science. And this is sort of a Kantian term, but I mean just sort of science as practice, or as we see it as philosophers. So on the one hand, we have the view from the inside. So sort of understanding scientific knowledge claims and scientific methodology from the perspective of the practice of science itself. So I have a little, idealized philosopher here sitting inside the observatory trying to understand what science has to say about the world. And on the other side, we have sort of the view from the outside. It's trying to understand the modes of thought and structures supporting scientific knowledge claims, scientific methodology, and the practice of science itself. So here I have a little idealized philosopher digging at the foundations of science, trying to figure out what they can find. So of course, this distinction is meant to be blurry. I'm not arguing that on the one hand, sort of naturalists, realists, empiricists, and instrumentalists are unaware of the concerns or worries that emerge when one looks at science from the outside, and vice versa, that relativists, idealists, constructivists, contextualists, all these isms are unaware of scientific practice as we find it. The sort of thought behind this distinction is to highlight the different questions that one can ask concerning science and the types of conclusions that one might draw depending upon the questions one asks. So to the extent that this distinction is useful at all in discussions of scientific practice more generally, which is, I guess, somewhat questionable, I think it's simply no longer tenable in the context of discussions of the history of theoretical physics. That is sort of the sorts of science that's done on a blackboard as opposed to in a laboratory. This was something that physicists in the early 20th century were acutely aware of, that the development of a new theory, one must simultaneously develop and defend novel methodological principles. And of course, the importance in this context of the role that mathematics has taken to play in the methodology of modern theoretical physics was paramount. So you can think here of people such as Helmholtz, Hertz, Duhem, Poincaré, Hilbert, Cassirer, Weil, Einstein, Eddington, Dirac, and one can keep going. And this is what I'll be focusing on today, sort of the problems posed by the application of mathematics and the methodology of modern physics, what we want to call mathematical physics. So before getting into some of the problems, I wanted to set out sort of, I guess, my unique wish list of what I would want from a form of realism, at least generally. I mean, the list isn't exhaustive, but roughly what I would be looking for. So, I mean, I guess you could call this a realist list or a naturalist list or some combination thereof. But in general, you would want a philosophy of science that would be in harmony with scientific practice. The philosophy of science should defer to science in questions of the structure and constitution of the natural world. And broadly speaking, the philosophy of science should be in conformity with scientific methodology, supporting in some sense the truth-conducive nature of scientific methodology and the manner in which secures unity in our understanding of reality, something vaguely like this. And I think that both structuralists and perspectivists make good on most of these claims. So in the context of structural realism, in the question, is it in harmony with scientific practice? Well, this is kind of the whole point of structural realism. So, I mean, generally speaking, I know that James Ladyman is here, hopefully. I don't know if I can see, but I'm going to try and talk more generally about structural realism at this point, and later on the talk deal more specifically with sort of ontological structural realism. So structural realism more generally, I guess I would characterize by paraphrasing Howard Stein in his wonderful 1989 paper, that science comes closest to comprehending the real, not in its account of substances and their kinds, but it's an account of its structure. And there's no question that modern theoretical physics is now largely based on the abstract mathematical structures that we take to characterize the natural world. So yes, I would say that there's not even a question whether or not structural realism is in harmony with scientific practice. In fact, I'd probably go so far as to say any account that fails to address the highly abstract mathematical nature of modern physics would be at odds with current scientific practice. So now the question, does structural realism defer to science in questions of structure and constitution of the natural world? Again, sort of this is kind of the whole point of structural realism. I would say sort of no pursuit better encapsulates the profound structural nature of modern physics than, say, the standard model of particle physics, right? So here elementary particles are defined through the group theoretic structures that characterize their properties. The standard model of particle physics is a gauge theory, i.e. a theory through which one appeals to local symmetry structures to derive the fundamental fields and their interactions. Thus, the nature of reality described by the standard model is, in a very fundamental sense, defined in terms of structural relations. And of course, Ladyman and Ross appeal to this example in defense of their view in the 2007 book. So yes, I would say structural realism does good on my second requirement. And the third, is it in conformity with scientific methodology? Again, kind of the whole point. So for the truth conducive bit, in response to the sort of pessimistic meta-induction, structuralists will highlight the fact that there's clear structural continuity through theory change. And some of this structure sort of can be responsible for the explanatory predictive success of the theory. Ladyman would argue sort of something like, all well-confirmed, this is a sort of quote, all well-confirmed modal relations expressed by old theories are approximately recovered by their successors. In addition to account for the no miracles argument, they would note sort of something that science, there's no miracle that science is successful if science tells us something accurate about the structure of reality. So maybe in Ladyman's account, science tells us about the objective modal relations among the phenomena, then sort of occasional predictive success is no miracle. But I want to come a little bit to the unity bit. So structuralists will argue that sort of science is in the business of, I forget the exact terminology that James used on Monday, but for some reason my memory, it's something like creating consilience networks of structural relations. And this is kind of the whole idea of the final theory program in modern theoretical physics, to come up with some sets of equations that can sort of codify and unite all of our theoretical understanding of reality. So in all of these respects, I think structural realism does quite well. The problem that I want to present is a question concerning what holds sort of all of this together. So I think that James's metaphor of triangulation is apt in this case. To define a consilience or to triangulate a set of claims, one presupposes a fixed framework through which these structures can be related. To take sort of, I guess, Paul Teller's example of the contrasting, or McKellar-Massini's example, I don't know which one of you guys did it first, of the contrasting properties assigned to sort of water and hydrodynamics, statistical mechanics, right? It's the overall framework of classical mechanics that allows us to relate these two claims together. So in the context of the broader theoretical changes in modern theoretical physics, my concern for the structural realist is to present an account of what holds these theoretical accounts of nature together. How is it that we tie them together into a unified picture of reality? Okay. So I'm not sure that structure is enough in this regard, I would say. Okay, so on to perspectivism. So is perspectivism in harmony with scientific practice. Again, this is kind of the whole point. When we go and look at science, we find that it's horribly discordant. There are various conflicting theories, various inconsistent models, and they all apply in certain domains under some limitations to give seemingly accurate descriptions of some parts of some phenomena in the area in which we're interested, right? So in taking on sort of the contextual nature of scientific knowledge, I would say that perspectivism is most assuredly in line with scientific practice. So perspectivism, we can trace it back, I guess, most famously to Geary's book in 2006, I think. And here Geary argues that the history of science has shown that all scientific knowledge is contextual in nature, in the sense that it is situated within a scientific framework. And given the contextual nature of scientific knowledge, Geary calls into question both the traditional appeal to objectivity and truth. But what makes Geary's perspectivism distinctive is its espousal as a form of scientific realism. He maintains that his perspectivism offers a sense in which modern science can still be said to say something about the world, i.e. that according to a given theory, the world appears to be roughly such and such. And this, he suggests, might be enough to support a genuine scientific realism. And in broad strokes, I mean, I think that this meshes quite well with how many scientists will view representation in scientific practice. So I would say that Perspectives does a good job in the methodology, accounting for scientific practice. And to defer to science and questions the structure and constitution of the natural world, again, I would say perspectivism does quite well. When you ask a question in physics, it's very unlikely that you'll get the same answer to, if you ask a question in physics, it's very likely you'll get a different answer depending on the person that you ask. Physics isn't monolithic, and in many cases, we seem to be unable to get a straight answer at all. One can think here of Margie Morrison's wonderful paper in 2011 concerning, I think it's the 20 different models of the nucleus that are still in use in physics today, all of which serve effectively in their domain of application, right? So what are we to make of all of this? So Paul Teller has argued, and I think correctly, that all scientific representation is imprecise and idealized. However, he notes that it may still be possible to have a number of representations of reality without giving up on scientific realism. And here I think he draws a really important analogy. Science, and he says science and human knowledge generally give us a vast plurality of representative tools, none of which work with both complete precision and accuracy. But a great many of the resulting representations, like not perfectly focused photographs, do give us real cognitive grip on things. And in endorsing a similar view, I think the perspectivist can make sense of the sorts of epistemic pluralism that one finds throughout modern physics. It may be that we have to abandon the claim of a God's eye view objectivity, but if this concession allows the perspectivist to account for the situated nature of scientific knowledge, so be it. Okay, perspectivism and the conformity with scientific methodology. Now here, lingering concerns remain about whether, let's say, Geary or Teller's perspectivism can make good on a realist claim. They both deny that there's a God's eye point of view, i.e. a complete and true description of the way the world is. The world that is being represented in Geary's perspectivism doesn't seem to be the traditional realist world of an objective mind-independent reality. Rather, it seems to be a world constituted by a given scientific perspective, beyond which no knowledge is taken to be possible. Geary's perspectivism is categorical, applying at all levels of scientific practice. Thus, it seems that Geary's perspectivism is at least seems to be in tension or fundamentally at odds, sort of the basic tenets of scientific realism. Things get a little bit better in Paul Teller's account, although I can't say I'm entirely able to give a fair reading of it. So Paul Teller in the 2012 paper gives a really interesting pragmatic theory of truth, whereby it seems that the coherence theory of truth of pragmatism is extended to the scientific enterprise as a whole. But it's still not entirely clear to me whether this sort of coherence is enough to support a viable realist claim, but it's something I'd be interested in talking about a little bit later. So in light of these concerns, Michele Massimi, in a series of wonderful papers, has sought to develop a new sort of perspectival realism, one which gives up the realist appeal to objectivity, but defends a realist account of truth, perspectival truth concerning a mind-independent reality. To motivate this perspectivism, Massimi draws on both the Kantian tradition and recent work on the perspectival nature of scientific modeling. She appeals to Kant, at least as far as I can tell, to defend a form of epistemic pluralism, but draws on the perspectival modeling literature to motivate a realist account of truth that supports this pluralism. Here, Massimi highlights the retention and continued success of scientific claims to the progress of science to support a realist account of perspectival truth. But again, my concern in the context of modern theoretical physics is what ties this sort of retention and continued success of scientific claims together through the progress of science, and how a perspectivalist can give sort of a realist account of these sort of meta-methodological principles. So to explore this in a little bit more detail, I want to address Massimi's account in more detail, but I take it that similar concerns may be found in all the various forms of perspectivism, and Paul can tell me if I'm wrong later. Okay, so here's my little picture of Massimi's perspectivism. So we have sort of three pictures of reality. I guess one, the green one here is sort of from, like, I'd say, classical physics, of the things that we're most familiar with. We have sort of the picture of reality from quantum physics, and the picture of reality that we might get in sort of general relativity or something like that. So despite the sort of plurality of theoretical frameworks and modeling practices, Massimi's perspectivism seeks to at least say something, to quote, about facts not being shaped by scientific perspectives or truth relativized them. In this context, Massimi draws an important distinction between two concepts that she suggests are often conflated in discussions on scientific realism, namely objectivity and truth. She suggests that one can accept and fully endorse that scientific inquiry is indeed pluralistic, and that there is no unique, objective, and privileged epistemic vantage point, without necessarily having to conclude that perspectives shape scientific facts or relativize truth. All the perspectival realist needs is an account of scientific truth that is independent of any appeal to objectivity, and this is exactly what Massimi puts forward in her 2016 paper. So at the outset, it's clear that scientific perspectives provide contextual truth conditions. But these contextual truth conditions only support a notion of scientific truth that is contextualized within the limits afforded by a given scientific theory, either past or present. These conditions do not license an interperspective truth, which would be required for a genuine sort of correspondence claim. And I'm not sure if perspectivists currently are grounding their account on correspondence claims, but it seems clear that at least in these earlier papers in 2016, this is the case. So Massimi suggests that if these contextual truth conditions are accessible across scientific perspectives, then we can characterize a perspectival truth qua correspondence, but contextualized and secured by a form of resilience and interperspective translatability. It is this sort of continuity across scientific perspectives that allows the perspectivist to determine whether a given scientific claim meets its original truth conditions from the perspective of our currently accepted scientific theories. The initial problem with Massimi's account is that it's not exactly clear how one can defend a genuine scientific realism as a result of these contextual truth conditions and their accessibility across scientific perspectives. Massimi suggests that we should understand contextual truth conditions as standards of performance accuracy, by which scientific claims are said to meet certain methodological constraints that define the successful application of a theory. In this case, the overarching methodology of science can serve to ground a notion of truth across perspectives. However, this may not be enough. And here I'd like to appeal to Ruger's 2016 paper, where he notes in the context of perspectival models that drawing on the analogy with different spatial perspectives onto the same object, The perspectival realist suggests that seemingly incompatible representations given by our models are in fact just representations of the same independently existing target system from different perspectives or points of view. The problem that I want to highlight is that to secure a viable realist notion of truth, it seems that the perspectivists must show that the set of claims that they hold to be true are consistent and reconcilable with the existence of unique mind-independent reality. So in response to these types of concerns, Massimi can appeal to her notion of scientific progress. She suggests that scientific progress can be characterized in perspectival terms. If we take scientific perspectives, not just as contexts of use, laying down, this is, I'm quoting here, so it's not my own word, laying down specific standards of performance adequacy for knowledge claims, but also, and most importantly, as contexts of assessment, offering standpoints from which knowledge claims of other past scientific perspectives can be evaluated in terms of their ongoing performance adequacy as set out by their original standards. Thus, scientific claims of our historical predecessors can be retained or withdrawn, depending on whether they continue to satisfy their original standards of performance adequacy when assessed from a subsequent perspective. Okay, so that's sort of my rough summary of structuralism and perspectivism. The point that I want to draw through all of this is that assuming that the progress of science leads to a consistent theory, i.e. that the set of claims that are eventually retained are consistent with the existence of a mind-independent reality, then what results from this notion of scientific progress appears to be a humble form of scientific realism. It's a perspectival realism that replaces the traditional realist notion of truth qua correspondence with an objective reality, with truth qua correspondence, establishes a form of resilience and coherence across the progress of science. This is simply the best we can do with the framework of our currently successful scientific theories, which are liable to change, of course. Okay, so I hope that that was somewhat clear to everyone, the introduction. I mean, the problem that I want to highlight is going to be much more pressing for the perspectivalist than it is for the structuralist. I think that there's sort of clear answers that someone like James could give to the concern that I'm going to address, but I'm not sure that they're entirely unproblematic. But the concern that I have in general, it relates to this sort of tension between the realist strand underwriting perspectivism and the sort of Kantian idealist strand underwriting perspectivism. Because I take it that it's reasonable to defend a form of realism that Massimi is putting forward by appealing to these standards of performance accuracy and inter-translatability and the continued success and retention of scientific claims. But the perspectivalist owes us an account of what supports this coherence and what supports the consilience of scientific claims. Okay. So my worries here are almost entirely stemming from my sort of love of the idealist tradition in the history of science. Oh yes, I should say also that it's not entirely clear whether or not structuralism fares better, but I'm going to come back to this sort of a little bit later. Okay. So my concerns about the role that mathematics plays in the methodology of modern physics really sort of find their basis in early 20th century idealist philosophy of science. And here I think Cassirer is one of the best examples. So in contrast to sort of the realist wish list that I presented earlier, I want to present sort of an idealist wish list, how an idealist would approach questions of knowledge, continuity, methodology, and practice in the context of the question of the fact of science. So Cassirer would say, well, the philosophy of science should begin with the fact of science and seek to determine the formal conditions for its possibility. The philosophy of science should trace the genetic history of scientific claims concerning the structure and constitution of the natural world. And the philosophy of science should clarify the constitutive frameworks underwriting the scientific methodology and the manner in which it secures the truth and unification of scientific knowledge. So Cassirer's neo-Kantian philosophy of science emphasized the constitutive role that mathematics plays in scientific thought. And he often sought to challenge the viability of a scientific realism grounded on the mathematical representation of nature. His general concern was that the mathematical formalism of modern physical theory as a symbolism harbors the curse of immediacy. In Cassirer's view, what is symbolized in abstract mathematics cannot be an exact copy of what exists. And it seems that scientific knowledge, whose task is to describe the real, this quote, and lay bare its finest threads, begins by turning aside from this very reality and substituting for it symbols of number and magnitude. End quote. When we analyze the conceptual systems which have facilitated the compression of physical theory through the comprehension of physical reality throughout history, we see that in appeals to realism, the instrument through which nature is understood often takes on a reality of its own. The concepts through which reality is delimited, for example, the notions of space, time, motion, are reified with a fundamental existence of their own. The solution, as Cassirer saw it, was to simply accept the fundamental mathematical constitution of the scientific conception of the natural world and give up the realist claim of representing a mind-independent reality. Cassirer held that the mathematization of nature serves as a necessary presupposition of scientific thought, but he did not believe that this in any way constrained the choice of mathematical formalism. It is here that Cassirer, in line with the Marburg neo-Kantian tradition, took a step beyond Kant in allowing for the revision of the constitutive framework of scientific thought. However, in allowing for this revision, Cassirer was forced to face the specter of a pervasive relativism. Thus, Cassirer held at the heart of mathematical physics lies the riddle of knowledge. In response to this riddle, Cassirer argued that the relativist abolition of the standard of objectivity does not entail the abolition of the difference in value and performance of various scientific theories. Scientific theories do not stand apart in their relation to the world, to be judged solely on their own merits, but rather as part of a progressive series. Cassirer suggested that it is this series and the hopeful convergence of the theoretical framework of modern physical theory that can take the place of an objective external reality. He argued here that we need not the objectivity of absolute things, but rather the objective determinateness of the method of experience, right? So, sorry, I forgot to click here. Okay, yes. So we need not the objectivity, but rather the determinants of the method of experience, right? So it's really striking the similarity here between Cassirer's argument and Massimi's, at least to me it was, right? Both are appealing to sort of the methodology of modern science to secure sort of an account of scientific knowledge. Whereas for the neo-Kantian, it's no problem accounting for truth. The question is objectivity. And for the perspectivalist, it's not really objectivity is the problem, but it's securing an appeal to truth. But they both appeal to the exact same sort of continuity through the methodological framework of science to define what it is they're going to be realists or about, or define the objective core of scientific understanding. So this formed the basis for Cassirer's appeal to a brand of neo-Kantian structuralism. And I know that Cassirer has at times been appealed to by a number of people, sort of forefather, I guess, of modern structuralism. I think I would agree with Heiss in saying you'd be sort of hard pressed to isolate the realist core of Cassirer. I think it's something interesting to talk about, but at least from my understanding of Cassirer, it's really hard to defend. But the basic disagreement between Massimi's perspectivism and Cassirer's neo-Kantianism is clear. While they would both maintain that scientific knowledge is historically and culturally situated, Cassirer holds that no knowledge is possible outside of the constitutive framework of science. In contrast, Massimi holds that such knowledge is possible, at least in principle. In defense of her view, she appeals to the retention and continued success of certain scientific claims through the progress of science to secure a sense in which they can be said to have some, I guess, grip on reality. However, Cassirer, at least as I understand it, would likely complain that the perspectivist realism seems to remain forever in the shadows. The interperspective accessibility of scientific claims, secured within the framework of the methodology guiding scientific progress, does not on its own entail that the claims that the perspectivist accepts correspond to the world, as opposed to the framework that Cassirer would argue underwrites scientific progress. And in response to this general Kantian concern, the perspectivist needs to specify the sense in which the methodological framework of modern science is able to secure a viable perspectival realism. So that's sort of the challenge that I take to emerge from Cassirer's critique of the general realist program in the context of modern physics. And to support this critique, I want to present a short, hopefully short case study. I think I'll have time. So I want to talk a little bit about something that I presume perspectival realists and structural realists would want to claim corresponds to the world in some way. And that would be something like the conservation of energy as a sort of law of nature. So the principle of the conservation of energy stands as one of the pillars of modern science. It underwrites large portions of classical physics and is to a large extent upheld in one manner or another in almost all branches of modern physics. Thus, the perspectival realist might want to suggest the principle of the conservation of energy is true. And I take Michaela to be saying this somewhat in her 2018 paper, although from a perspectival Humean best systems account, which is a little different, but I think the point that I'm trying to make should still hold. So the inter-translatability of the principle across scientific perspectives, its adherence to the standards of performance accuracy, and its retention and continued success through progress of science clearly all support the perspectival truth claim. However, I want to argue that the retention of the energy conservation laws, let's say in the transition from a static to a dynamical space-time theory, can only be defined within the mathematical formalism of modern differential geometry. There's something about our mathematical understanding of the phenomena that is essential to our relation of these two scientific perspectives. And you can see the sort of Cassirian critique that I'm trying to put forward here. So the space-time structures of classical physics, quantum theory, special relativity are all static. In each theory, if a system is subject to Hamilton's principle, then it is well known to anyone who has taken, I guess, even second year undergraduate physics that the symmetries of the Lagrangian will correspond to the existence of conserved quantities. In particular, it's easy to show that if the Lagrangian does not explicitly contain particular coordinate dependence, then the corresponding canonical momentum will be conserved. To quote Goldstein in the famous 1980 book on classical mechanics, the absence of the explicit dependence on the coordinate means that the Lagrangian is unaffected by the transformation that alters the value of the coordinate, is said to be invariant or symmetric under a given transformation. It is clear why this is called a symmetry in the Lagrangian. The transformation of space and time map the Lagrangian on itself. They are automorphisms that leave this structure unchanged. And the reason why I'm talking about symmetries, I'm talking about natural law, is that Neuters' first theorem generalizes this result and demonstrates that every continuous symmetry in the Lagrangian corresponds to a conserved quantity. Now, Neuters' theorem has been addressed at length in the philosophical literature, Brading and Brown, 2003, Ehrman, 2003, Brown and Holland and Butterfield, and I don't want to get into sort of the conceptual foundations of Neuters' theorem here, but I want to point out that to ensure the invariance of the Lagrangian, one has to presuppose that the symmetries correspond to symmetries in the underlying metrical structure of space-time. The reason why this is the case is it's easy to see. If the definition of a symmetry requires that an object be mapped onto itself, then there must be a consistent means of defining the relevant notion of sameness. The motion must clearly take place along a continuous isometry in the space-time. That is the concept of an isometry that allows us to define the relevant notion of sameness or congruence. So to understand the problem posed by the development of dynamical space-time theories, I want to quickly, I think I'm running a little bit out of time, but I'm going to try and just do this really quickly. It'll be worthwhile to take a closer look at how we define isometries in a dynamical space-time. So the initial concern is that the comparison of a geometrical object, such as the metric or any such thing, at different points requires a definition of distance. It is the metric itself that provides this definition, and certainly we cannot use the metrical properties of a space-time to study the metrical properties of a space-time. This would be equivalent to using a meter stick to study how meter sticks change from place to place. Rather, we need a way to characterize the change in a metric brought about by motions in the manifold that doesn't actually rely on the concept of the metric itself. And this is where the concept of Lie dragging and Lie derivatives come in handy. And I need to try and skip because I'm going to be a little bit behind. So basically, we can just fill a manifold with a congruence of curves, which are just sort of a bunch of lines that don't intersect. And we can use the congruence of curves to define a notion of translation in our manifold and study the properties of geometrical objects as we move them about in our manifold. So the idea is that we can use, okay, so if we can Lie drag our metric tensor fields across the manifold and find that they do not change, these isometries are defined by the Killing vector fields of the manifold structure, and the Killing vector fields uniquely define sort of, I guess, the isometries of a space-time. So then we can now use these structures to study conservation laws in a dynamical space-time theory. At the outset, it's clear that we can only derive global conservation laws in space-time structures that possess the relevant Killing vector fields. This is not typically a problem because in classical mechanics and quantum theory, the relevant space-time structures are maximally symmetric and possess all the required Killing vector fields to define global conservation theorems. However, in an arbitrary dynamical space-time structure, there'll be no Killing vector fields and no isometries. So there'll be no globally conserved quantities and no global conservation laws. Now, all of this might not be a serious concern so long as we can show that the dynamical space-time structure of, so let's say, general relativity has the relevant Killing vector fields. And here's where all the problems start. So the Killing equations are elliptical PDEs, they're acausal. So the very imposition of sort of global isometries on a space-time general relativity violates the causality constraint of the theory. And we don't even really think that sort of the local arrangement of energy and momentum in our environment is symmetric. So we really have no reason to believe that there would be any sort of exact global symmetries. However, despite these concerns, we can still secure a local account of the conservation of energy within the shared geometrical mathematical framework of modern physics. This shared framework whereby all space-time structures are taken to constitute a differentiable Riemannian or pseudo-Riemannian manifold allows for the local specification of the typical Lie symmetry groups. The regular nature of the Riemannian space-times of modern physics ensures that typical conservation laws will apply locally, and as long as we have some reason to believe that our space-time structures will be reasonably well behaved, we can derive some broader, more global claims from that. Thus, it seems that we would be able to give a viable perspectival account of this notion of retention and continued success. However, it is only from the perspective of modern differential geometry that we can define the sense in which the conservation of energy laws found in static space-time theories are retained as local laws in dynamical space-time theories, such as general relativity. On a neo-Kantian account, we can simply suggest that the underlying geometrical mathematical framework serves as a constitutive framework for modern physics. And that's what secures the law of conservation of energy, or the objectivity of the law, the conservation of energy. However, on a perspectival account, I think to a certain extent also on a structuralist account, it's not immediately clear what role we should assign to this broader mathematical framework. Okay, so that's the sort of, I guess, major claim, and I think it presents a pretty clear dilemma. So I think I have 4 more minutes, and I'll try and stay under. So in addressing the fact of science in the context of modern theoretical physics, I think the perspectivist is faced with sort of 2 hard choices. Either they can abandon their thoroughgoing structuralism and accept that there's some sort of underlying mathematical formalism for physics that allows us to sort of correlate these claims. Or they can abandon their realism and claim that this mathematical framework is itself nothing but another scientific it seems that neither option is going to go all that well. But I think there is kind of a way out. And I'm short on time. I have a sort of a long spiel, which I could maybe get into if someone's interested later. But I think that there's a way out. And I think it's kind of a way out that would push perspectivism more in the direction of structuralism. Because I think that there's something of the similar problem that plagues structuralism, about how it is that we sort of correlate mathematical equations over time, and how is it that we define these limiting relations that, that we want to appeal to represent, say, the objective modal structure in reality. And that would be to appeal to some sort of, I guess what many people might call crazy, but some sort of a Platonic Pythagoreanism. And I mean, I don't know the extent to which Ladyman and Ross are already endorsing such a view. I know that there was an interesting discussion with Tien Cao about whether or not structuralism collapses the distinction between mathematics and nature altogether, and how one reads, I guess, that debate would answer what you think about this. I take Ladyman and Ross to be defending sort of mapping account, whereby the mathematical structure of physics maps onto reality in some appropriate way, or the modal structure of reality in some appropriate way. But anyway, I don't think it would be entirely crazy to secure a form of perspectivism by an appeal to a general Platonic Pythagoreanism. And in doing so, I think one could appeal to very good support amongst early 20th century and even mid 20th century physicists. So here is a famous quote from Dirac. So Dirac argues that there's no logical reason why the method of mathematical reasoning in physics should be possible at all. But one has found in practice that it does work and meets with reasonable success. This must be ascribed to some mathematical quality in nature, a quality which the casual observer of nature would not suspect, but which nevertheless plays an important role in nature's scheme. And of course, Dirac was on to defend a really interesting account of mathematical beauty as the key to unlocking sort of nature's secrets. And one could also appeal to more modern physics. Here's Feynman. When learning about the laws of physics, you find that there are a large number of complicated and detailed laws. Laws of gravitation, of electricity and magnetism, nuclear interactions, and so on. But across the variety of these detailed laws, there sweep great general principles, which all the laws seem to follow. Examples of these are the principles of conservation, certain qualities of symmetry, the general form of quantum mechanical principles, and unhappily, or happily, I guess in our case, the fact that the laws of nature are mathematical. And I have a whole spiel going back to Nietzsche, but I think on my clock I'm out of time. So that is where I will end, and then thank you.